And we are now recording. Let's get the slideshow set up from the current slide. And turn on the projector. And wait till the screen goes off of black. And wait till the Windows symbol to go away. Get out of presenter mode. All this stuff I have to do before we can actually start. Okay. All that done. And can't make up its mind where it's going to go. And it's not going to give me my icon, so I'm going to have to use the pen here. Okay. All right, first, any questions on anything we have covered up till now? Okay. Now, just a reminder, in Chapter 11, which is I think where we started off, right? We did 11.1 and 11.2. Now, we did a little bit more, but that's most of what you're responsible for in 11. Let me just go back and review that. 11.1, 11.2, I know you're responsible for those. 11.3 polar coordinates, not so much. If you need that in your majors and stuff like that, you've been exposed to it, use that to follow up. 11.4 is area and arc length in polar coordinates. We kind of went by that too. 11.5 was conic sections. Okay? I don't think I'll ask you any specific questions on that, but don't forget that. We're going to be covering that again in 12.6, or following up on that in 12.6. So I won't ask you questions on that, but you will have it in 12.6. And then 11, and that was it for Chapter 11. Now we're done 12.1 and in 12.2. And once we finish 12.2, we will kind of, well, we'll hit that when we get there. All right. No questions? Now, where we left off last time, we had just finished vectors, introducing vectors in 3 dimensions. And from here, we're going to move toward parametric equations of a line. And this is 3-dimensional equations, okay, of a line. And here's where we'll start with this. We'll blow this up. Because it's off-centered some, I will do it here. Hopefully that almost covers the whole thing. Okay. Now, the easy line. Okay? A line through the origin. Okay? Whatever vector v leaving through the origin, a line in that direction is just going to be a multiple of that vector v. Okay? In the same direction v, if that multiple, or t, that parameter t, is positive, opposite direction if it's negative. Okay? But that's how you write a line that's going through the origin. If you can find any vector v that's in the same direction, then the vector r will be some multiple of that vector v. Now, lines that do not go through the origin, okay? Like this line, green line here, L, okay? L for line, I guess so, yes. I don't even know what kind of L that is. It's weird looking L, but anyway. So let's say we have that same vector v that we had before, okay? And in fact, we have some multiple of that vector v, tv, origin, okay? But we want a line that's parallel to this line, but it's not going through the origin, okay? It's going through some other point, P0, okay? Now, think of our vector addition. This point P0, that's a point. 3-dimensional coordinates, not components, okay? vector that goes from the origin to P0 would be the vector OP0, okay, from the origin to P0. You know what P0 is, you know its coordinates, so you know the vector. All right. You also know this vector V and this parametric extension of V, TV, that this is parallel to. Well then, this R of T, this is vector R as a function of that parameter T, is that OP plus TV. And that then gives you a parameterization of that vector R of T. Depends on what the displacement is from the origin. That's what the vector OP tells you. That's not part of this vector. That just gets you up there. And then add to that multiple of V, TV. So there's a line through a point in the direction of another vector. Okay? That's it. Okay. Now, trying to. Okay. This initial vector V, they really didn't say much about it, but they said that vector V, let that be the vector, and this is a vector, so it would be, I'll write this down. Of course, if I write it down, it's going to shrink it, but I think it's worthwhile doing so. This vector V here, or here, either place, is the vector A, B, C. Okay? And this vector is the vector A, B, C. Those are the X, Y, and Z components of that vector V. Then this TV that we have here is then the vector TA, TB, TC, because it multiplies, it scales up each one of these components here. Okay? Now, that point P0, oh, I'm on the wrong page. So I'll say we've already done that. Okay. Let's see if they named that point P0. Yeah, I thought so. This point P0, that's a point now, and that's a point X0, Y0, Z0. Point, parentheses, coordinates. Okay? Now, the vector P0 from the origin there, and I would be tempted to write it in that same color, but I'm afraid that doesn't show up too well. Let me try to do this color and see if that shows up a little bit better. Then this vector P0, it would have components X0, Y0, Z0. Okay? The point P has coordinates set, but because the vector OP0 is from there, then its coordinates are, components are X0, Y0, Z0. Okay? Now, if we're adding this vector to this vector, that's adding those two together. So the components are, for this vector, let's go back and make this one green. Dark green, okay? Okay, so this vector R of T then would be, I guess it matters which you do first, X0 plus TA, Y0 plus TB, that's tuberculosis, Z0 plus TC. All right, top cap. Okay, so that would be your line L, written in vector notation, will be x0 plus TA, y0 plus TB, blah, blah, blah. Okay. Now, goodness gracious, I'm cold. Another way, excuse me. Y'all awake yet? Okay. What's that? Yeah. Wow. Okay. Another way you could have expressed this is the vector x0, and this is basically what I did, x0, y0, z0 plus t times the vector ABC. That's vector ABC. That's how we came about doing it. Okay? Each of its components are then. I think we beat that to death. Let's go now to their equation of line. Say again? Yes. A big, old, heavy one. Okay. Goodness gracious, I'm cold. Now, on top of everything, I had my flu shot today, so so if I start feeling really bad, I shouldn't. I've never had a problem with it. Well, where did it go? Yeah, quit that. What's that?
Cold and congestion and stuff. It being cold in here,
Yeah. So the last class, I actually finally had to go down and clear my head because I was hardly able to talk. But I'm feeling a little better now, but it's still, and you see, this blows right on me and it drops me nuts. Okay, equation of a line, and now this almost sounds like slope-intercept, kind of. No, point-slope. This is like point-slope. It's called the point-direction form. Not quite the slope, but direction. Point-direction form. So some line L through some point, P0, that's the point part, and that P0 has coordinates, point having coordinates, x0, y0, z0, that you can't see here, but I'll scoot that over so you can, in the direction of, so here's the direction part, vector v. Vector v is some just any old vector, parametric vector, ABC, okay, is described by, here's the vector parameterization, okay, and I think I mentioned to you before, because I'm used to say parameters, then I usually say parameterization. There's no E in there. It's parameterization. Okay? So I don't pronounce it very well. The vector parameterization of this vector we're describing here, that line E, L, is R of T, is that vector OP, the vector OP from the origin to this, which is x0, y0, 0 vector now, plus TV, that's some parameterization multiple of the vector v, t times ABC. So that's the straightforward. The parametric equations describing that vector would then be the x component of this vector, R, would be x0 plus TA. The y component of this vector, R, would be y0 plus TB, and, or BT, they're doing that first. And the z component of this vector, R, would be z0 plus CT. Okay? Now, the parameter t can vary anywhere from negative infinity to positive infinity. And that will exactly define that line. Line being infinite. Now, if it's a line segment, then you chop it off somewhere. But the line is infinite in both directions. So there's your parametric equations for a line. Okay. I think this is the figure they use to describe example 4. Okay. Okay. Now, Victor's here. One new and one emphasized announcement I made to everybody else, and I want everybody to hear it. They are always, and especially early fall term, looking for tutors. If you have made an A or a B in any course, any level of any course, you qualify to tutor in that course at that level. Okay? I think all of you would be great math tutors, but you don't have to do math. You could do any course you've made an A or a B in, you can tutor. Just down the hall here in room 202 is Monchelle Hollins. She's our tutor coordinator on this campus for SSS. They pay you, what do you say, 8 something? 8? Yeah, 8 something, a little bit better minimum wage per hour for tutoring. And it's totally at your schedule. When you want to, when you can, when you're available, when you're free. If there's someone there that's looking for tutoring, you can do it. So a great opportunity, I think, to not just give something back, but to improve your own skills. That's where I really learned math the best, when I was trying to explain it to somebody else. Okay, and then the second one is we are still looking for people on the math team, and as Cameron pointed out, you can see what some of the typical questions were, because we had our first session yesterday afternoon, and will be every Tuesday, Thursday afternoon until the Thursday right before that, the contest, which is what? But yeah, it's early October. That weekend, the 8th is It's either the first or second Thursday. The one right before the meet, I'm going to be out of town. Okay, so but except for that, every Tuesday and Thursday afternoon, 3:30 to 4:45. Last time we were down in 259. I imagine we'll just keep meeting there. It seemed like the room's free there. Come on over. But if you want to see what it was like yesterday, go to YouTube, like you're going for this course, and you'll see the other playlists there. Look for the one that says Math Team. It was a pretty short time that we had together, and we were doing things from scratch, but hopefully just building up people's kind of comfort and knowledge base so they could do it a lot faster, hopefully, in the competition. But it's a fun thing. It's nothing bad, nothing negative. Should be a fun event. All right, example 4. Find a vector parameterization and the parametric equations for the line through the point P0 is 3, -1, 4. This doesn't look like what we're dealing with here, okay? Now, this is the paragraph right before this. I don't think there's a figure for here. I'll leave this figure up here and I'll talk from it, okay? So we're going through the point P0. Let me go back to black here. Okay, so our P0 here is the point 3, -1, 4. Is that negative? Yeah, 3, -1, 4. So just to get an idea of where we're talking about, if this were the place that we're interested in, you'd be going out here 3 units on X, back 3 units on Y, and up 3 units on Z. Okay, so it would be a point somewhere over here. Okay, behind the X-axis, because Y is negative, but right of this plane and above this plane. Okay, but behind that plane, the YZ, XZ plane. Okay, so that's where we're starting. In the direction of the vector V, and vector V is the vector represented by, now these are components because this is an angle bracket, 217. Okay, so in the direction of that vector, okay, now that vector, you go out 2 here on the x-axis, plus 1 on the y-axis, and up 7 here, so it would be a vector that heads up this way. But through the point that's back here somewhere, okay, you have to come back to here, and in this direction, but going through that point. So there's your deal. What would be the vector? That's what they're asking for first. Vector parameterization of that vector. We'll call it, sorry. Okay. Okay. We'll call it vector R of some parameter t. You could use any parameter you want to. They usually use t. So how would you express that vector R? Okay. The vector OP0, which would now be a vector, but with the same coordinates that those are components, that these are coordinates, because it's from the origin to that. So that would be 3, -1, 4, plus, since we're using parameter t, times vector v, 2, 1, 7. Now that's all you have to do to express that in the vector parameterization of the vector you just described, going through the point parallel to that vector. Okay? Now, the second part said, and the parametric equations. So what would be the parametric equations? What's your x of this vector? X would be 3 plus 2t. Your y would be -1 plus t, and your z would be 4 plus 7t. Okay, that's your vector. That's your parametric equations for each of those components. Okay, so let's see if they got it right. They carried the first one more step that would be intermediate to these two. Yeah. So they took this one more step, which is what I did last time, but they didn't, so I didn't do it here. This would be the vector 3 plus 2t, comma, -1 plus t, comma, 4 plus 7t. Which basically then has those components right where they belong. Okay. That was example 4. Any questions on that? Okay. What if, on the other hand, we are asked to give a parametric equation for a line through 2 points? Now, this was sort of like your point slope formula for a line in 2 dimensions. It's called point direction. What if you wanted to get the parameterization for a line through 2 points? Just to keep from confusing them, I think I'll clear the writing. Is okay? Y'all got this? By the way, all Y chromosomes again today. Sorry about that. Okay. Let's clear all this ink. And we'll do P. This is one reason I want to do it. We had a P on the other one. We didn't P on it, but 1, 0, 2. And Q. Another point. And Q is 2, 5, -1. Okay. Now, I don't know if this is helpful or not. Since I got a graph here, let's go through it. This would be 1 here on X, 0 on Y, so we don't go in either direction here, and then we go up 2. So here's one point right here, okay, coming out from there. The second point is coming out 2 on X, 5 on Y, -1 on Q. So here was one point, there's another point down there. We want the vector between those 2 points, okay? Now, it didn't specifically say what was our direction on it, so you could really choose either direction you wanted to, because you see your t, your parameter, plus or minus, that'll take care of the direction for you. All right, so how do you reckon you're going to do this? Okay. Not quite. Okay, think this. When you had point slope, which is what we did last time, and you went to 2 points, what was the first thing you did? Not the distance, the slope between the 2 points. Well, actually, the line between those 2 points. I mean, it was the slope. And how do we do that? Change of y for change of x. Okay, but now we're doing the vector between those 2 points. That's what gives you a direction now. That's why they don't say slope, they say direction. If you knew the vector, what's the vector between those 2 points? You can name it if you want to, or you could just call it, I'm going to do PQ. It could be QP. It doesn't matter which one you put first. Like I said, the parameter will take care of the sign. But what would this be? That's now a vector, so what would that be? Second? I can't hear. 1, 2 minus 1, comma, 5, comma, isn't it negative 3? Yeah, negative 3. You're doing from one to the other, 2 minus 1, 1, 5 minus 0, 5, negative 1 minus 2, minus 3. There's the vector, and pick either one of the points. It doesn't matter which one, P or Q, and do your parameterization from there. I think they probably choose P. Yeah. Let's see which one. No, yeah, they choose P. Doesn't really matter. So the vector parameterization, what would we call this? They don't really give it a name. Yeah, oh yeah, R of T. That's what we called it before. R of T would then be what? One. Second? No. That's the part that you multiply. The vector is multiplied by the t. You start with the point. So 1 plus t, it's this thing times t. That plus this thing times t, basically. Oh, I'm sorry. Okay, no. Okay. That's the first component. Second component, 5t, not plus, 5t. Third component, or 2 minus 3t. It doesn't matter how you do it. I usually write the point first and then the other. Let's see what they did. Yeah. They first wrote it as the point plus vector t, ultimately writing it 1 plus t, 5t, 2 minus 3t. Yeah. Now, did they also want the parametric equation? Find the... Oh, yeah, that's what they asked for, the parametric equations. So they didn't really... Well, the parametric equations are just these. X equal 1 plus t, y is equal to 5t, z is equal to 2 minus 3t. Okay, that's it. Oh, and since this is a line, minus infinity less than t less than positive infinity. You really should put that on every one. If it were just a line segment, then you would limit that to the values that you want it to be. Kind of like they did here. I guess this is the same illustration they had before, not the previous example. There was that initial vector that was the initial point P, so that's your OT, so that's R of 0, and then R of 1 would be here, 2 there, 3 there, that's getting longer and longer, but negative 1 you'd be going in this direction. So that goes infinitely for all values T. Okay, so if you only had a segment, you would start again wherever those values would be. Okay. And that's what they talk about next. To obtain the parametric equations for a line segment between P and Q, so if you only wanted to stay between P and Q, then what would be your limits on the parameter? How would you get to point P? T is equal to 0, 0, 0. 1, 0, 2. That's how you get that. So there would be the left-hand end. How would you get to the next one? What would that be? 1. Yeah, T would be 1. It would be 1 plus 1 is 2. 5 times 1 is 5. And 2 minus 3 times, so that would be negative 1. Yeah. Okay. So for just the segment between these 2 points, so that was usually written as PQ with a bar over it, not with an arrow over it, that's the line segment. That would be the same parameterization, but then your T would be less than or 0 less than or equal to T, T less than or equal to 1. That then gives you the line segment. Okay. I forgot they were going to do something like that. The parameterization of a line is not unique. We're free to choose any point P0 or Q0. In other words, if we had chosen Q0, then that parameterization would have been 2 plus T, comma, 5. Yeah, I was trying to find it, plus 5T, comma, negative 1, minus 3T. That's also the parameterization of the same line, okay? But of course, if you wanted the line segment, then this would be going from, I believe, negative 1 to 0. Yeah, 0 would certainly give you the second part. Negative 1 would give you the first part. So the same parameterization would give you the same line segment. It's just different limits on your parameter. Okay. We're free to choose any point P0 that's on the line, and we can represent the direction vector by any non-zero multiple of scalar multiple lambda v. However, any 2 lines in R3 coincide if they're parallel and pass through a common point, so we can always check whether the 2 parameterizations describe the same line. Okay, so let's do example 6. There's no picture here either, but there will be something that we can use. All right, I'll come to that in a second. Show that R1, this is a vector, as a function of parameter t, which is 1, 1, 0. That's some random point that's on the line, plus your parameter t times the direction vector is negative 2, 1, 3. And R2, also a vector, also a function of t, is negative 3, 3, 6, plus your parameter t times 4, negative 2, negative 6. Okay? It's saying show they parameterize the same line. Okay? Now, in my mind, all we have to do is find a value t that this equation would give you that point. Okay? Then you know this point's on the line and that point's on the line. Okay? And then find a t that guarantees that point is on the line. And if you've done that, these 2 points, if you have 2 points, how many lines can go through 2 points? 1 and only 1. So that has to be the same line. It may not be how the book does it, but that to me is the way to do it here. So basically, you've got some equations here. We know that -3 needs to be 1 minus 2t. Okay, so let's solve that. What do we get? I got that from this point being a combination of those, right? You see? So what does that give you? Subtract 1 from both sides, and you get, subtract 1 from both sides, you get -4 is equal to -2t, so t would be 2. Okay? Let's see if that works for all of them. 1 plus 2, sure enough, is 3. 0 plus 6, sure enough, is 6. So that guarantees this point is on that line. Okay? Now, if we can show it goes the other way as well, let's do that. Well, this would say that -3, you tell me. Plus 4t, 1. Okay, what t would produce that?
1.
Okay, t equal 1. 4t equal 4, so t equal 1. Let's see what t equal 1 does down here. 3 minus 2 is 1, and 6 minus 6 is, there they are. Both points are on both lines for the proper t. Same t for all the, you have to keep that t for all 3. It shows they are indeed the same. Now let's see. That's, to me, is the straightforward way to do it. Is that how they did? It looks like so. They only did one set of equations, so I guess they're happy with that. Okay. That just showing they're both on the same line, so you don't have to do it twice. Okay. We did it twice, showing it. Okay. Now, these this was the set of parametric equations we used for that. Okay. So I don't know why they picked that equation. We had done that equation earlier and everything else, but that's the equation they used. Well, that's what they showed. That this point was on that line for the same t. That showed that these 2 points are on the same line. If they're on the same line, that's the only, I mean, you can have different parametric equations, but they reduce to the same thing. Okay. So, basically the same thing. Now, let's go to the next issue, and that would be, oh wow, what's that one? Okay, do y'all see this anywhere? Where is that? Oh, I see. That's equation 9. So that's part of this next problem. So let's just use this page. This is equation 7. No, I'm sorry. It looks so similar to this one. There was equation 7. That's the one we just did. Here's equation 8. We'll get there in a minute. All right. Let's do this one. Intersection of two lines. Determine whether the following two lines intersect. Here's R1, a vector as a function of t, and that's equal to 1, 0, 1 plus t times 3, 3, 5. Okay. R2, another line, is 3, 6, 1 plus t times 4, negative 2, 7. Okay, now, just so you don't think that these are the same line, let's just do sort of what we did before. If you tried to say, are these the same line, then you would say 3 is equal to 1 plus 3t, and that would be t being 2/3, I believe, right? And if you did t equal 2/3 here for the second one, that would be a 2 here, you got a 6. So no, these 2 points aren't on either one of these two lines. I mean, this point's on this line, this point's on this line, but this point's not on that one, this point's not on that one. Okay, we didn't show the second one, but it's not. Okay, so they're not the same line, okay? Different lines. So the next issue is, do they intersect anywhere? And what that means is there one value of t that contains a point on both lines. And it doesn't have to be the same t, remember, okay? So they have two. Let's just call this one T1 and this T2, okay? That's what they're doing, okay? Now, if there's a point that these two lines intersect, let's say that point is the point X, Y, Z. And we expect no more than one point. Since these are not the same lines, they're not going to have an infinite number of points. If they do intersect, it's only going to be in one place. Two lines can either be collinear, or they cross once, or they never cross at all. Okay? So those are our options. Since we've already shown they're not collinear, that means all the points are in common, then the most they can have is 1 point in common. So let's say it's that point X, Y, Z. Okay? Well, then this would say that X would have to be equal from that first equation, 1 plus 3t1, right? I'll put these in. Really don't need them out there, but the important thing there. And we'd also have X having to equal 3 plus 4t2. Okay? That same X. What does that say? That says that 1 plus 3t1 has to equal 3 plus 4t2. Doesn't it? Okay? So basically that tells us that 3t1 minus 4t2 is equal to 2. You see what I did? I said, I hope I did it right. Nope, I didn't. It's minus 2, I think. 4t1 minus 3t2 is equal to minus 2, that is. Okay, minus 2. Okay? Now, let's do the same thing for y. the y value from the top equation would be y is equal to 3t1, and that same y would have to be 6 minus 2t2. Okay? So then I would say 3t1 plus 2t2 would have to equal 6. Guess what? I think we can solve that, can't we? What would that give us? What's that?
I said I wanted to do C.
We will. That's how we're going to check. Okay? You can do Z anytime. Oh, no. Okay. Let's subtract these equations from each other. Subtract this one from the one above. That wipes out your T1s. Let's do it the other way. Let's subtract this one from this one. Okay? That wipes out your T1s, and that gives you 6T2 is equal to 8. So T2 is equal to 4/3. Okay, and if T2 is 4/3, plugging back in here, 3T1 minus 4 times 4/3 is equal to -2. That would be 3T1. Did I choose the worst equation for this? Yeah, let's back off and not do that. No, actually, no. I don't think I'll get, yeah, you're right. Okay, I was looking at the wrong one. Okay, that would give me T minus 16/3 is equal to -6/3. Notice what I did there? Get everything in terms of thirds. So 3T1 is equal to 10/3, right? Adding 16/3 to both sides. So T1 is equal to 10/9. All right. So with T1 equal 10/9 and T2 equal 4/3, now let's do that Z and see if we get the same point. You get 1 plus, is it 50/9? Yeah, you're plugging that in. 50/9, okay? And that would equal 9/9 plus 50/9 is 59/9. Let's do the same thing on the second one. And that would be 1 plus 70/3, right? Oh, wait. No, goodness gracious. I'm getting all crossed up here. Okay. Okay, let's see. All right, let's back off again. Let's see. T2 is 4/3. So 1 plus 4/3 times 7 is 21/3. So that would be 3/3 plus 21/3 is, that isn't working out well, is it? 24/3, which would be 8. Yuck! Let's back off a minute here.
28/3.
You may be right. Oh, wait, I'm sorry, I looked at the wrong one. This is a 3 here, not a 1. Sorry, that's right. So 3 is 9/3 plus 21/3 is 30/3, which is still not doing it right.
I thought it was 28/3.
Ha! All right, let's back off. I must have made a mistake somewhere here. The two lines intercept if there's existent parameters T1 and T2 such that R of T1 is equal to R of T2, so for blah, blah, blah. So 1 plus 3T1 equal 3 plus 4T2. Got it? That gives you, oh no, the second one then is 3T1. Yeah, 3T1 equals 6 minus 2T2. We got that one right. Okay. Let's solve the first two equations. So, okay, I guess the very first equation I botched up here. Let's.
But in that second, what were we doing at the end there for Z?
Okay.
It's supposed to be 1 plus 7T2 times.
Oh, you know, I had it right the first time, didn't I? That was a 2, a plus 2. I don't know how I messed it up. 3T1 minus, I had it right the first time. That's where I messed up. Okay, so this would equal, sorry, right at the very beginning. I had it right and changed it. Okay, this would equal 4. Okay, and so T2 is equal to 2/3. Sorry about this, folks. Oops. Two-thirds. All right. Now, I bet you the second one I got right, but let's just see. No, I plugged in. Yeah, I know I got this right too. Yeah, let's change all those. Sorry about this. Eraser. This will be a 2/3. Okay. Let's get my pen back. Okay. 2/3. This will be minus 8/3. Oh, that's a plus 2 there too. So that's a plus 6/3. So 3T1 is equal to 14/3. And T1 is equal to 14/9. Yeah, that doesn't get any better, does it? All right, and we did the same thing over here. Don't tell me I botched this one up too.
Well, I mean, you had the wrong T2, so.
What's that?
If you had the wrong T2, that bottom one's going to be wrong. With a 21/3 should be.
No, but if I did the same thing here that I did up there. No, that's right. I'm sorry. No, that was getting that formula. Okay. So what I do here is then calculate the Z. So let me do a lot of erasing here. Okay. So all this mess is wrong is out of here. Okay. Sorry about that. Okay. We got our T1 and our T2. Okay. Yuck. Okay, now we're going to deal with the Z. That's what we're trying to do. 1 plus 5 times 14/9. That would be 9/9 plus, is that 70? Is equal to 79/9. Okay, let's do the next one. 1 plus T2 was 2/3. That's 2/3 times 7. And that would be 1 plus 14/3. thirds. This is still not coming out right. That's 3/3 plus 14/3 is 17/3. Ah! Oh! Guess what? They don't cross. I was assuming here they did intersect. And they said determine whether the following intersect, not where they intersect. They don't, okay? These two don't match. That means the two equations don't intersect. Okay. What's that? Yes, I was trying to prove the impossible, okay? And sure enough, they don't, okay? All it said, determine if they do. Nay, they don't. They are not parallel lines. They're what they call skew lines, but they never cross, okay? So don't think that two lines in space, if they don't cross, are parallel. On a plane, if they don't cross, they're parallel. But in space, they could be parallel or they could be skew. These are skew lines, okay? Never even coming close to each other, very close to each other, but they're definitely not crossing. So sure enough, they do not. Since these two, there is no solution, the lines do not intersect.
So you find the T1 and T2 and then just plug it into Z and show that it doesn't work?
Right, that's what we just did, yeah. That there is no Z that makes that work. Okay. So, sorry, I misread the question. We want to do the preliminary questions here. Let's see. Let's see what they did. This is the first part. I should have gotten onto here. They said, if this is true, then there is some T1 and T2. They don't have to be the same T's because those are just parameters. They can be starting with different things, but that should work. So we did one equation with the X values and one with the Y values, and we got what the relationship had to be. And then we tried to plug that into the Z value. And these were the equations we did. Okay. That's the one we got here. 3T1 minus 4T2 is equal to 2, not minus 2. And this was T1 plus 2T2 is equal to 6. And we didn't ever do that one, or I didn't think we solved for the first two. Well, they don't show the solution. I think they may do it in the book, but they don't show it on the slides. And anyway, these are the lines, okay, right there. Okay. R1 is up here somewhere, going on this very little way. R2 is down here, but not touching. They cross like this, but not touching like that. So there is no point. We found where the T1 and T2 would have to be the same, but the Z wasn't the same. Basically, what we found was R1 and R2, the T1 and T2 were the same here, but then when we got up here and plugged in for Z, one Z was up here, one Z was down here. Not intersecting at all. Okay. With that done, well, let's see. Is there anything else on here? Whoa, where is that one? I guess so. I sure don't see it in this one. Do you? Yeah. All right. Line through 2 points, P and Q. It seems like what we were doing earlier. But we didn't have that figure. That looks kind of like example 5, but they're not the same. Yeah, so don't sweat that. Okay, This must have been in the old book because it's in the previous edition. Does anyone have the previous edition? Old one. Is this, do you find those in there? Okay, what, do y'all have some more examples in that? Is that example, what, 8? 7. So you have an intersection of two lines? That was example 6. Okay, what was your example 5? Parameterizations of the same line. Okay, so this is the parametric equations through a line with 2 points. Okay, they didn't give us a block like they did for the point direction form. They did it like this. Okay, we just did the example without having this form. So, okay, that makes me feel a little better. This is your review summary, the right-hand rule again. Okay, and here's your equation for the sphere of radius r and the cylinder. We did this last time, so I'm not going to harp on this anymore, but I'll just blow it up so you can see it. We came up with that. Actually, what I did was then divide every term on both sides by r squared, so you had it equal 1 over there. You do the same thing here, and that almost looks like the equation of a circle, unless you're told this is a 3-dimensional thing, and then that gives you the cylinder, circular cylinder of that radius. So we already did that one, and that was the last slide. So let's do the preliminary questions, if you choose. What is the terminal point of the vector 3, 2, 1? Here's the vector v. 3, 2, 1. That gives us creative components here. Based at the point I've lost it. P is equal to 1, 1, 1. Notice that's a point, so that's in parentheses.
So would it be 4, 3, 2?
Yes. The terminal point, let's call it Q, would then have to be 4, 3, 2. Does everybody see that? Because the difference between those two is that vector v. Right? Okay. You want to make sure the back of the book got it right? This is the 12-2. 12-2 is 4, 3, 2. They got it right too. Good for them. I'm so proud of them. Okay. Okay. Number 2. What are the components of the vector? This sounds like a crazy one. The components of the vector 3, 2, 1 based at the point P, 1, 1, 1. Say again?
Wouldn't it be the same thing?
As what?
3, 2, 1?
Yes, those are the components. It's the vector that, those are its components, okay? It was sort of a tricky question. 3, 2, 1. Those are the components of the vector v wherever it's based. That's the point. Okay, number 3. Has nothing to do with those anymore. If vector v is equal to minus 3 times vector w, then choose the correct answer. A. V and W are parallel. Okay. B. V and W point in the same direction.
It would have to be A.
Right. Okay. They are parallel to each other. Okay. But they can't point in the same direction because this shows it's in the opposite direction. Okay. exactly opposite direction, and V is 3 times as long as W, which is immaterial. But this says they're parallel to each other. Wherever they are, they're parallel to each other. Okay. Good deal. I don't think that's in the back, but let's see if it is. A. Oh, yeah, it was A. Choose A or B. Yeah, A, for sure. Number 4. Which of the following is a direction vector for the line through P and Q? Is it the same P and Q?
Yeah.
No, not quite. Okay, here's P is 3, 2, 1. Not a vector, but a point, 3, 2, 1. And here's Q, and that's the same as P was before. This is a point, 1, 1, 1. Okay. Now, which of the following is a direction vector for the line through those 2 points? Is it A? A would be 3, 2, 1. That's vector. Yay or nay? Nay, no way. 1, 1, 1. Can't happen. So I'm guessing C. C is 2, 1, 0. Okay, yeah, because it's the difference between them. Okay, 2, 1, 0. So it better be C. 2, 2, 4, C. Got it. That means yes in Spanish. Okay. Number 5. I think I'll clean this out. Anyone need this any longer? Erase all the ink. We'll go to the top. Number 5. How many different direction vectors does a line have? How many different direction vectors does a line have?
Sounds like a tricky question.
What's that?
Sounds like a tricky question.
Yeah.
Because a line goes in 2 directions.
Okay.
But a vector is a line. But it's just more of a ray.
Right. But you see, so far, all they've told us a direction vector is a vector that gives us, so let's say we had, let's see, direction vector. V is called a direction vector for line L, okay? Well, any multiple of V,
It'd be infinitely many vectors.
infinite many, because you have infinite number of multiples of V. Yeah. And they can be plus or minus. They would both do. Now, that's what I would interpret they're looking for. Let's see what they say. Infinitely many different direction vectors, not different vectors, direction vectors. Yeah, because you could just multiply by any number, positive or negative, and you have an infinite number of numbers. Okay? And finally, number 6. True or false? If V, okay, that's a vector V, is a direction vector for a line L, is a direction vector for line L. They do this strange looking L. That's nowhere close to an L. They'll do that. Vector line L, okay? Then, minus V is also a direction vector for line L. I would see. Because we haven't said that L's direction means anything yet. So I would say, yeah, yes. True, absolutely. All right, homework exercises here. Do either 1 or 3 or both, either 5 or 7 or both, either 9 or 11 or both. Do 13, only one like that. Do either 15 or 17 or both. Any of the odds 19 to 23. either 25 or 27 or both, either 29 or 31 or both, any of the odds 33 to 39, either 41 or 43 or both, either or any of the odds 45 through 59. Might want to do a few of those, okay? And if those aren't challenging enough for you, you certainly can do any of the other further insights and challenges, odds 61 through 67 that you choose, but that's not required. Okay, any questions on 12.2? You're responsible for 11.1, 11.2, 12.1 and 12.2, and what am I doing? In show, discard. Okay, hang on just a moment here, and we'll move on to 12.3. Now, most of the time, I don't test on 12.3 because I've never, see, this is material that should have been at the end of Cal 2, okay? I've never gotten there in Cal 2, and we've always had to come back and cover it, so I will test you on this one, okay? 12.3. Never done it before because we've always run out of term before we ran out of time, and but it's always been in Cal 2. I was trying to go quickly here, but this is important stuff, so let's get it covered now. All right, I'll try to go fairly quickly here. Dot product, okay? Have all of you taken physics? Any of you haven't taken physics? All of you have. I think you're familiar with dot products then, aren't you? Okay. Say again?
To an extent, yeah. I don't think we've ever done it in free space.
Okay. Well, maybe not. Okay. Well, it may be worth it. Dot product, V dot W, it always has a vector, dot, another vector. Now, that dot is sort of a times, but it's not every kind of times, okay? In scalar multiplication, you can either use parentheses, dot, times sign, anything. They mean the same. In vectors, a dot product is different from a cross product. Okay. Hopefully you know that already. Here's what a dot product is. If you have vector V, which is A1, B1, C1, and vector W, A2, B2, and C2, those are the components of each. The dot product of any two vectors is a scalar, not a vector, okay? And it's defined this way. The dot product of these two vectors would be A1 times A2 plus B1 times B2 plus C1 times C2. Those are numbers. Those are scalars. You multiply them, they're scalars. You add them, they're scalars. This is a scalar, okay? That's what a dot product is. Dot product of two vectors produces a scalar. Make sense? Kinda? Sorta? A little bit? All right. Here are properties of the dot product. Okay?
It'll zero property.
Yeah. I love that zero vector. It's one of my favorites. Okay, I didn't need it that far, but we got it. Now, this is a zero vector. Notice it's bold, not the number zero. Zero, you don't dot it. The number zero, you don't dot it with a vector. You just multiply it by the vector as a scalar. Okay? This is a zero vector. You can dot that. This is 0, 0, 0 dotted with A, B, C. So that would be 0 times A, which is 0, plus 0 times B, which is 0, plus 0 times C, which is 0. Same as V dot vector, 0 vector, which would be A, B, C, dotted with a 0, 0, 0. And it still comes out the number 0. These are vector zeros, that's the number 0. Okay? The sum of that is 0. Is that the only way you can get 0 from multiplying from a dot product? If one of the two vectors is 0.
They're inverses.
No, if they're perpendicular to each other. Yeah. Yeah. Okay, if multiplicative inverses. Yeah. Well, additive inverses. Okay. So, let's go to commutativity. That means, does the direction matter? No, it doesn't. V dot W is the same as W dot V. Doesn't matter because what you wind up with is a scalar number. And if you V dot W gives you a number, W dot V better give you the same number, okay? Now, pulling out scalars, okay, it sounds like you're pulling out teeth or something. Okay, if you have lambda V, lambda being a scalar, multiplied by a vector V, dot that with a vector W, that's the same as if you had the lambda multiplied by W, V dotted with lambda W, which is the same as if you pulled the lambda out all together and dot it and multiply that by V dot W. I say it's the same. There's just a little bit of nitty-picky type stuff that makes it different. This is scalar multiplication, right? Multiplying a scalar times a vector. This is scalar multiplication, multiplying a scalar times a vector. But this is just multiplying two scalars. Because when you multiply two vectors, you get a scalar. This is just plain multiplication. But that's just real picky. It gives you the same result, nevertheless. This is a vector. Dotted with a vector gives you a scalar. That's a scalar. That's a scalar. Now, the distributive law. If you dot the sum of two vectors, that's U dotted with V plus U dotted with W. Okay? Or if you put the sum in front, V plus W dotted with U, that's V dotted with U plus W dotted with U. Which, by the way, those are exactly the same. What's that? They are the same thing. Okay, because these two are the same, those two are the same, you're adding two scalars. Okay. Now, here's one that you're going to use a lot. Okay? Relationship with length. You dot a vector with itself, square magnitude squared. And if you think about this, this would be, if this is ABC and this is ABC, this would be A times A plus B times B plus C times C, A squared plus B squared plus C squared. And the square root of that is the length of the vector, magnitude of the vector. So basically, you've got the magnitude squared. We will use that quite a bit later. That's one thing this is worth going over for. What's that? It's a lot like Pythagorean theorem, yeah. Well, that's how we get the length of a vector. Yeah, use a Pythagorean theorem. So this is another way to get there, dot to vector. The vector with itself. Right. Okay. I think we're going to need a little bit of background here because this is just something pulled out of the air. This is example 1, so let's do it. I think. Yeah. Verify the distributive law. In fact, let me go back to this one. I can't blow it up, so verify the distributive law, this first one right here. Ooh, how did that happen? I haven't written anything yet?
No, this PowerPoint.
I guess not. Okay. We're going to verify this one right here, that distributive law. Okay? For these vectors. Vector U is equal to 4, 3, 3. Vector V is equal to 1, 2, 2. Used to be a defense we ran in basketball, a zone. And vector W is equal to 3, negative 2, 5. we didn't use it much. It wasn't a very good defense. Okay. So we want to verify the distributive law doing this. So what that says is U dotted with the sum of V plus W. So let's do V plus W first and tell me, okay, U we know is 4, 3, 3. Going to dot that with the sum of V and W. Can you tell me what that is? It's what? 4, 0, 7. Okay? You added those together? Add these two together. 4, 0, 7. Okay? Now, let's dot those two together. 16. I could do that one. Okay. 21. And what does that yield? 37. Okay, let's do the other side. U dot V. What's U dot V? This dot that. What's that? Say again, 4 plus 6 plus 6. Is that what you said? 16 plus U dot W. What's that one? 12. Say again? 12 minus 6 plus 15, and that would be 6 plus 15 is 21. Add those together, and what do we get? 37. Ding, 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 ding. It works. Okay. That's all they ask us to do there. What's that? Oh, okay. You close your book like that. I thought we were running out of time. Stop that. 7 minutes, okay. Now, let's go to this. This is important. I think we can do it in 7 minutes, maybe less. Okay. Oops. Try it again. Still didn't make it. It's going to be 7 minutes till I get this right, you know. It's as tight as I can make it. Ah, if I only hit the right key. I keep getting no. Ah. Sorry, folks. Late in the day, things get squirrely. There we go. I can't quite get it all on, but I got close to it. Okay. As mentioned above, the dot product is related. Oh, where did they say that? It says as mentioned above. Where did they mention that? I don't see anywhere they did. Oh, it may have been on the side. Yeah, okay, so one of the side notes. No, I don't see it there either.
Maybe it's just talking about VW.
Okay, but whatever. V.W is related to the angle between V and W. This angle theta is not uniquely defined because, as you see in this figure, both theta and 2 pi minus theta can serve as this angle between V and W. Furthermore, any multiples of 2 pi may be added to, you remember this from trig, okay? All right. So, but if we define theta to be something between 0 and pi, then that does make it unique, because this is obviously outside of pi.
That's supposed to be theta.
That's supposed to be a theta there. Goodness gracious. Oh, when I go to write it in, of course, it's going to shrink. Okay, this is a theta, not a pi. Okay, in the book they have it right.
Yeah.
Well, I thought they did. Oh, I turned the page already. Yeah, they have it right in the book. Okay, now, with that being the case, why are we bringing this up? Well, there's a relationship between the dot product and the two vectors and the angle between them, and that's coming up next. Do we have time for it? Okay, the angle between two vectors is chosen to satisfy this. Okay, satisfy theta has to be between 0 and 2 pi. 0 and pi. So that means the obtuse or acute angle theta, okay, can't be beyond pi. You say we are out of time?
We got
5 minutes. Oh, okay. All right. But you have to go. I understand. All right. With that said, then here is that relationship. Okay? And sometime, in fact, I'm trying to recall, it seems like my first introduction to the dot product was through this relationship, not through the one we just had earlier. But that's just me. Okay. Let theta be the angle between two vectors v and w, and that means the smaller of the two angles between that, the one between 0 and pi. Okay? Then the dot product between two vectors, v and w, is the magnitude of v times the magnitude of w times that cosine of the angle in between. Or another way of saying that is the cosine of the angle in between two vectors is equal to the dot product divided by the product of the magnitudes. Okay? So this gives us a whole new way of calculating an angle, because it's pretty straightforward. V and W can be given by components. If you got their components, you can get the dot product, you can get their magnitudes, and you can define the angle in between this way. It'll always be between 0 and pi, because that's, when you take the inverse of that, you'll be between that. So this is another way of expressing the dot product of two vectors. It's not just the sum of the product of their components. That is indeed true, but this also gives you another way to calculate it. If you know the angle, this is the easier way, perhaps. Okay. Now, it seems like to me this next slide is the last part of this slide. Okay? No. Wait. Sorry. The next word slide will be, this will be ways of looking. Oh, let's see. What are they saying here? Not really clear what, except if you have that as an angle theta, and you have the length of these three sides, so what? You could be doing law of cosines or law of sines or something, but I don't know why that's there. This is pretty clear why this is there. If you add v plus w, you would get this vector up here, and v minus w would be, in other words, w plus v minus w would be v. So yeah, this is how we did our vector subtraction. One way of doing it. What different? Oh, okay, this is a proof, and that's exactly what we're doing using the law of cosines on this. Okay? I'm not really all that hankering to do the proof. Do y'all like proofs? You want to do the proof? Walk through it? You're okay without it? Most of your engineers, right? You don't care about proofs. You want to solve problems, right? Okay, I thought so. Me too. All right. This was the one that is just like the previous one. No, it isn't. Oh, okay, this is another form. Okay, this is also in the proof. And it's this basically comes straight out of the law of cosines. Okay? That this side squared is equal to this side squared plus that side squared minus 2 times the cosine of the angle in between times the this squared, this magnitude of this. That's the law of cosines, right there. If you go back and look at the previous slide, that's the law of cosines. Okay? This was our C. C squared is equal to A squared plus B squared minus 2 AB cosine angle in between. That's exactly the law of cosines. So that's why they have that one up. And then, amazingly, they do this. Okay? This V minus W, which was our C squared, this thing, was V minus W dotted with V minus W. And then the previous one, the V squared was V dotted with V. No, I'm sorry. What they're doing is expanding this. V dot V minus 2V dot W. This is just expanding this. Plus W dot W. And this part is V squared. That part is magnitude W squared. And this is that. Basically, you've just about proven the theorem. Are we out of time now? Okay, sorry about that. Just when it was getting to be so much fun. Okay, it was always fun, wasn't it? Okay, let me give you a few homework assignments in this section. It won't be many, I don't think. Oh, it's a fairly short section. So this will be any of the odds 1 through 11, I think you can do. Yes, easily. Any of the odds 13 through 17. Either 19 or 21. Any of the odds 23 to 27. And we'll stop there. We'll pick up the rest of those later. Good deal. We will see you. Oh, have a good weekend. That's right. Working on that test? Oh, no, you don't have a test yet. We're getting close to that. All right, we will end this here.